So today we have a rather mixed bag. We're starting off with two HEP talks on the LHC. Then we move towards severe weather and finish off with robotics. I want to thank Caterina and Ben a lot for the first two talks today. There was illness, unexpected travel, another illness, and they have filled in perfectly with these talks, and I think they'll go nicely with each other, one setting us up for the other. And so I will give it to Caterina. Thank you.
So thank you very much for the invitation and for the attention. I understand that you really like acronyms, because HCP at LHC, and I'll show you that we like three-letter acronyms, TLAs, a lot as well. So the talk today is heavily based on material from a number of people here, and it's also partly based on a workshop that precedes this by a few years, the dark matter, sorry, the data science at LHC workshop. And this is a series that the Simons Foundation has also had interested in. And I'm going to talk about what it means to make real-time decisions at the LHC. It's a fairly personal view, and it's mostly considered as a series of discussion points rather than me talking, so please interact. I'm giving you a fairly high-level view of things, as I'm not necessarily an expert in all the things that I'm talking about. But we have some experts in the room, and if you have questions that I don't know how to answer, I'll just shut them off. So let's start with the outline. So I'm going to talk about 5 points. First, I'll introduce you to the Large Hadron Collider and Atlas. This doesn't need too much of an introduction. Most people know what this is. And then I will go more in detail on the LHC experiment trigger systems. So what is a trigger? It's not great to talk about triggers in this political climate right now, but maybe we'll rename it eventually. But this is what decides in our detector whether to keep data or not. So this is the key point for this talk here. And then the last part is going to be on how and why to make the most of LHC data. I work on dark matter, so the examples that I'm going to use are related to dark matter. And I hope this makes the astrophysicist in the room feel a bit at home. And then finally, I'll conclude with something that links more with the talks yesterday, how to do the monitoring and what it means to monitor detectors and data taking. So let's start with the not quite real time. This is a graph that has made the rounds. It's from The Economist. And this is the various particles of the standard model of particle physics in years on the x-axis, from the concept, from the theoretical concept, to the discovery. So there's only 2 real-time discoveries here, if you consider the fact that they were discovered before they were theorized. But most of the other particles took a while. And especially the Higgs boson took the longest somehow. It was theorized in the 60s, and then in 2012, we found evidence for it. So the first point to take home here is that particle physics discoveries requires very large instrument and sometimes a lot of time. So it's not an instant discovery. So what does it take to discover a Higgs boson? And let's see if I can make this happen. Yes. So you need a particle collider and something that makes a lot of particles collide. Not a lot at the same time, not necessarily, but in a very high frequency particle collider. Because these kind of processes, what you see on the y-axis is the number of events, and on the x-axis is the diphoton invariant mass that is connected to the mass of the Higgs boson that you see here. This is the Higgs boson bump. This is very rare. It's, if you have 600,000 collisions per second, but only 1 in 10 to 13 or so contains a Higgs boson. So you need a high rate collider to begin with. You need also a detector that is able to select and precisely measure photons. And here I'm talking about ATLAS and CMS mostly, but there's also other detectors at the LHC. And each of those has millions of readout channels, so you can think about rate times number of channels. This is a very large volume of data. And then you need the people. You need teams that operate the detector. You need to calibrate the photons or all the other objects that fake photons, for example. And then do the data analysis, so come up with this nice data minus fit, where the Higgs boson actually appears.
I have a question. Is the data on every single energy channel independent of the other energy channels, or are there some?
So you mean this is the bins, right?
But is there correlated noise in the adjacent bins, for instance? Or
yeah. So yeah. you have to deal with the correlations, the bin by bin correlation, and it can come from many different sources. Like the energy scale, if you don't measure the energy of a given photon precisely, then it might migrate into a different bin. And this is one kind of correlation. There's many others. You can also decide to make better than real-time discoveries here. And here, I don't know if there's any theorists in the room that might get offended. But there's, and maybe you've heard in December 2015 that there was, in the same distribution as where the Higgs boson was discovered, there was a small excess. And you can possibly see it by eye, possibly, maybe, if you really squint. And here is it's a website that it's not just for high energy physics, it's for more, for many other fields where you have the announcement of such plots, because they only become public after a really intense peer review and internal vetting. So you make an announcement, and then this happened on the 15th of December at 14. And then at 16:47, someone had 7 pages about it. So that's great. This is real-time data analysis. Or someone picked up a paper from a printer. One of the two. So this was just a facetious point. But so what is real-time analysis at LHC experiment? This is a definition that might or might not work. It's not a quantitative definition. But this is what you do with a first-pass data analysis that you have to do in short time scales with a limited amount of information. And it can influence further data taking. So this is the definition I'll use for real-time analysis. And the first part of this talk will concern the data analysis done within the trigger system, where you have to decide whether to record a data event or not. And the timescales that are involved are of the order of microseconds for the lowest level of the decision. So let's start with looking at the Large Hadron Collider in its experiment. And you know that it's 27 kilometers of circumference collider that collides protons against protons. And then collisions are recorded and analyzed by 4 main experiments. And I'm going to talk mostly about CMS, LHCb, and ATLAS. So the first thing I'll try is to show a video. What might or might not work, yes. So you've seen, some of you that have seen Ilya's talk yesterday have already seen this. But I think it's pretty spectacular to see how deep underground these experiments are. So this is a 175-meter underground experiment. It's a tunnel where the protons circulate. And there's 4 really large experiments, we'll see the size of them later, where the particles that are accelerated up to very, very close to the speed of light end up colliding. And then it's the experiments that see the products of these collisions. And this is one example of one collision. You see the tracks and the energy deposits in the calorimeters that then get 600 million times per second get then distributed to computing. So we'll see the computing part later. And now let's stop a little on the CMS detector. You see how big it is compared to people here. And this is called compact. So it's not quite, but it's more compact than ATLAS. But this is tens of meters detectors. And another impressive thing is that you see that there's many different technologies and many different parts of this detector, many sub-detectors that are used to measure the particle properties. And the information is reconstructed for each collision event. And what you call an event is the combination of all the information from all this detector in that gets turned into particles.
Kind of naive question, but
of course.
To what extent is coincidence necessary? Coincidence at a very high time resolution necessary to interpret events?
It's used.
The detector.
Yeah. So it's used within the detector in well, there's 2 ways you can use it. You need to have some coincidence of your electronics with the collisions of the LHC, and you can use timing in that way. Although, of course, the response of the calorimeters and the response of the tracking is not necessarily instant. So you have some buffering that happens within the subdetectors. But at least you have a timestamp for each of the collisions. And then there's a thing that I'm not going to talk about, but it's quite a nice development of LHC detectors is timing detectors. So you can actually use time information, very, very precise time information.
For an individual collision that has products.
Yeah, so you can measure the time of when the particle arrives in your detector and then use that information for doing analysis.
Along the same line, what's the radius, what is the radius of the detector in units, or relative to the time separation between the events?
That's a question that requires pen and paper.
But there's events still coming out of the detector, right, when the next event is happening?
Yes.
Yeah, that's happening.
Yes, so you get pile-up from events that have gone through previously, affecting the signal of events that are being recorded
Right.
now.
So coincidence is kind of, it's coincidence on the light cone, not literally coincidence.
Yeah, it's not, you have ways to store the event and understand what out-of-time pileup is what he's talking about. It's not the simultaneous collisions, it's the one from before and after. Yeah. So another remarkable thing of these detectors is that you can't quite see the scale here, but this is the number, the fraction of channel that work. And in a detector like this, there's millions and millions of channels. And all the subdetectors have more than 95% of channels that actually work. And we're quite far into the first run. We started running in 2010. So I think it's marvelous that things work. Maybe I'm pessimistic in this way, and it's all thanks to the people of the experimental collaboration. So I've taken some pictures of just a small part of Atlas, CMS, LHCb, and ALICE. But you can imagine that these are really large experimental collaborations, up to 3,000, 3,500 people per experiment. And also you probably understand that our author list sometimes is longer than the paper itself. And that creates some interesting sociological questions that we can discuss in a coffee break. All right, let's go on to the data delivery. So here we are talking about a quantity that is called the integrated luminosity. And that is the amount of data that is collected. There's also another quantity that is the center of mass energy. This is the number 7 to 13. And that is how many, that you can discover more massive particles if you have more energy, essentially. So these are the two figures of merit of a collider. How much data it gives you and at what energy it gives you the data at. And you see here that in the progression from 2010, you can't quite see on this scale the data, the amount of data given compared to 2017. So there's orders of magnitude more, 1 or 2 orders of magnitude more data delivered in the same time in 2017 with respect to 2010. So we are now in a production mode for the LHC. It's running very well. It's giving us the data that we need. So what does the machine parameter mean for experiments? We have up to, at the moment, 30 megahertz bunch crossing frequency. So there's one collision every 25 nanoseconds. And the consequence is that detectors need both fast electronics but also good buffering. You can't quite keep the whole event and process it in 25 nanoseconds. And the other thing is that if you want a lot of collisions, think about being on two opposite sides of the room and trying to throw tiny, tiny ping pong balls at each other. You'll never hit. These are protons. So this is a thought experiment that makes me think you need a lot of protons if you want some of them to collide because they're small. So there's about 3,000 bunches per beam. Each of them has 10 to the 11 protons. And there are 600 million collisions per second as a consequence, in the hope of producing something interesting such as the Higgs boson. So the consequence is that, yes, there will be one collision that you want among many that you might not want. So this is called pileup. And the current data taking, we have up to 70 simultaneous collisions. But for the high luminosity LHC run, we plan to go up to 200. And usually one selects only the most energetic, as that has the higher chance of containing something interesting. But all the others are also interesting. So there's a democracy of collisions. You know, something interesting can come up. So I don't know if Ben is going to talk about this, but that's something that is quite fun to do. How to make the most of this pileup that people think is just noise, it's junk, we have to discard it. No, there's still interesting information there. So this is the picture that we saw in the talk yesterday, the amount of LHC data in CDs. Now it's probably going to be used stack, pen drives, I don't know, or racks. But so these are some numbers that one can come up with. 40 million collisions per second up to. Multiply that times the amount of data per collision. So I'm thinking about one of the big experiments, basic data packet. It's 1 megabyte. And then you get to 40 terabytes per second. You multiply that by the approximate running time of the LHC. It doesn't work all the time, but it does work day and night when it does. And then you get to quantities that are bigger than Facebook in 2014, but of course there's always a bigger fish, as Craig's talk said yesterday, of course, there's other commercial company that makes more data than the LHC. But they also have more money than us. So that's one thing that we need to think about, how to frequently process all the data from all these channels of the detector. And this includes also calibrating and aligning the detector so that the data that comes out is already ready for analysis. And then we need to select only the interesting events. The problem in principle, though, is that we don't know what interesting is in advance. As we've seen before, there are particles that have been discovered before they were theorized. So if we had just based our selection on what we think exists, we would have missed those. So there's some parallels with astrophysics, and one is that there's this fire hose team. This is a slide that I pulled from an LHCb talk, where there's the trigger system of the experiment is like drinking from a fire hose. And then yesterday, 2 days ago, there was the LLST talk at this workshop that says, are we building a fire hose? LST is the data producer. So that makes me conclude that the LHC is also one of the data fire hoses that we have. So it's nice to think how to transform it into a nice community fountain. So another parallel with astrophysics is that to try and to set the scene of what the trigger does. So we've seen that the LSST data broker spots the interesting events, and then what you want to trigger a follow-up with another instrument. And the limited resource in this case is the follow-up instrument time, and that also costs money. And the cost of not following up, what happens to you if you don't point the instrument to the place where LSD data broker had told you to, is that you're missing some interesting transient. For the LHC, it's something similar. You spot an interesting event with a very coarse data reconstruction, and then that can trigger the recording of the event for further analysis. The limited resource in this case is the data taking bandwidth. This is one of many. Also, computing is a question, but let's just think about that for the moment. And the cost of not recording that event is that event is the LHC has produced it for you, but you've discarded it. So it will cost LHC money somehow, because you built this machine, to recreate that category of events, because you need to build another LHC if you forget to record a given category. So it's a fairly heavy cost for particle physics to not optimize the trigger system.
I have a question on that, and please correct me if I'm wrong, but for LHC to spot an interesting event, they already have to have the definition of interesting characterized, right, in their trigger mechanism. Is it flexible enough to catch? Okay.
I think that's what I'm covering in. So there's systems, LHC is going towards a triggerless readout, because for them the definition of interesting is different with respect to Atlas and CMS. Okay. But yeah, that's the fear and terror of all experimentalists. Okay. I'm not triggering on the events I want. Okay. So how do you define interesting? And this plot is a bit busy, but this is the transverse energy or the particle mass of the process that you care about. And this is in units of barns, because barns, of course, is a big thing, and the cross-section is a big thing, apparently, but it's really tiny. It's 10 to the minus 27 or so centimeters. This is the cross-section of a process, and the number of expected events is a product of the luminosity that you can collect times the cross-section. So this is the cross-section and the luminosity are directly proportional to how many events you see in your detector. So here, in terms of cross-sections, this is the LHC, somehow the LHC cross-section. It's order barns. And then what is interesting to Atlas and CMS is 6 orders of magnitude lower. You have the W and the Z at their mass. And then you have the Higgs boson that is still 3 orders of magnitude lower. So there's a big difference between what you could take and what you actually want to take. For LHCb, the situation is slightly different, because the cross-sections of the processes that they're interested in are much higher. So they have a different kind of problems. They want to take all possible events, because you could look for something that is rare in this sea of C. Sorry for the pun. But the other problem that both Atlas and CMS and LHCb have is that, what if we're aiming to discover a new rare process that is just buried in one of these high-rate backgrounds? And we can't distinguish at the trigger level. You just have to take it and do the analysis later. With this principle, you just discard it, because you're not taking all the events. So let's have another look at the standard model in that sense. There's two things that I wanted to take out from this plot. That is, here you see the cross section, and there's many orders of magnitude between the inclusive, all the events that one can take with a proton-proton collision, and what starts being interesting, so the W production here. And these are called frequent processes now. Now we have plenty of W, plenty of Z. That's a very different situation in which the first W was celebrated at UA1. Now we don't know what to do with them. But there's processes that are more rare but still quite frequent, and you have this production of TT bar events, single top. Then you start producing two bosons at the same time, and you go down a few orders of magnitude as well. So in these cases, you have one interesting event every 10 to the 6th, roughly. This is your ballpark estimate. And the other thing that is interesting to see in this plot is that you have the theory on the back of the data. So the data is the colored, and the theory is the gray box. And you see that pretty much everything is well lined up. So is that a good thing or a bad thing? Many people would just cherish a theory that tells you such precise things about the nature of your fundamental particles. We hate the standard model, and I don't understand it. Yeah, the point is that one thing that I want to point out is that the standard model is really remarkable in doing what it's supposed to do, and we are probing it with very high precision. But there's another side to it. Why are we doing that? And that is, we're trying to solve some problem that it has. And there's a number. I'm just bringing up two. One is, this is Murayama's definition of aesthetic art problem. The standard model is not pretty as is, because the Higgs mass needs a large correction that you don't know where it comes from. So it's, they say the Higgs boson mass is fine-tuned. And the theory that it's fine-tuned is not beautiful. There's also other problems that I like more, because there's something that we see. And an empirical problem is that we have something that is dark matter in the universe. So unless gravity is wrong, but maybe it's right after the gravitational wave measurements, maybe there's a new particle, and that new particle is not in the standard model. So this is a large problem of the standard model, not being able to describe 75% of your universe. So one can think about the standard model as a low energy approximation of more complete theory. And there's a lot of different theories that can explain those shortcomings. But none of them is yet favored by data. We don't have any evidence of physics beyond the standard model in LHC data. And they can all give very different detector signatures. Some of them are buried in the high rate background. Some of them are rare but unusual. So making the most of LHC data really means to be able to enable discoveries by ensuring that all categories of these events are selected and recorded. Now I'll show you the LHC experiment trigger system, and since I'm going a little slower than expected, I will let you watch the video by yourself, which is possible. Well, maybe not. The presentation wants me to see this. Okay, but this is maybe interesting because it shows you how the trigger works. There's a first pass that is an electronic preselection that passes a number of events, a fairly large number of events, and then puts them onto a software system, generally, that select more and assemble all the information from all the subdetectors. So there's these two levels. There's a first electronic, just hardware level to make a coarse decision, but fast decision. And then there's a second level that's a high-level trigger. And then after the high-level trigger has made a decision, then everything gets sent to computing centers. And then the tape storage, and then to the LHC worldwide grid.
And what fraction of the down select happens in the first? Oh, I think you're about to say.
Yeah, that's what I'm saying here. So how do you trigger? And here I make the separation between the online world, so this is closer to the detector, and the offline world when you recorded the experiment, the event, and you can analyze it later. So the first step is a fast hardware selection that is 100 kilohertz for Atlas and CMS and data taking rate. And then there's a computer farm that does the second step of the selection and reduces it to about 1 kilohertz, which is the limit that we can. This is a hard limit. With the current technology, we can't record more than that. And it's partly it's because we can't store it. We could possibly record more, but we don't know where to put it. So these are the current trigger systems in Atlas, CMS, and LHCb. And here it's just some numbers. You have a 40 megahertz bunch crossing, and then in less than 2.5 microseconds, you have to reduce the data taking rate to 100 kilohertz. And then you have a longer time once you have fewer events for doing a software decision of the high-level trigger. And these are farms of approximately 20,000 cores, probably more now. I've not updated the most recent numbers. And then you go to storage at 1 kilohertz in case of Atlas and CMS, and slightly higher for LHCb.
Excuse me, is the kilohertz, that's events per second?
Yeah.
Okay.
So this is a more detail of the Atlas trigger. I'm not going to go into details of every step, but one interesting point here is that there's every single detector will give information out. So a very important part of the trigger is combining all these different parts of information. So how do you parallelizing and multiplexing are a big part in all these different in all the different systems. And the big challenge for data acquisition is also reading out all these channels that come from the detector. And that's why some upgrades are done on the readout side to improve the trigger.
How many bits of information is there in an event?
I'm not sure what you mean in terms of...
What are you storing?
Everything, if we can.
Energy?
A lot. So you can go from really raw detector information, and you save it, for example, the cells.
Okay.
Or you can do a high level. It's a tiered architecture for what we store. And I'm sure Tony knows more than I do. But still, it's you can have everything, and then you can have just the final state particles. You can be anywhere in between.
Okay.
So do you ever? So you're throwing out, if I think I did the math right, basically 1 out of every 4,000 events you're saving, so the rest you're throwing out.
I thought more.
Is that more than that?
It's 40 megahertz to 1 kilohertz.
Oh,
Yeah.
right. So more. Okay. So, are you ever storing data in a lossy format? So you do compression of the data that
It's already done. Yeah, it's already done in there.
Is that a lossless or lossy compression?
Maybe Paolo wants to. I mean the technical details for the data, but I don't know what you mean with lossy or lossless. Where you throw out a bunch of information.
You eventually decide to save. I assume you're trying to save everything about it because you think there's something potentially important about it. But there are other events that you might want to have saved, but you don't have enough space for it. Is there any value in storing a lossy version of all of that information?
Yeah, so that's the main point of the talk, I think, in this case.
So rewording that, you have the trigger mechanism is a highly biased sampling mechanism.
Yeah, you can call it like that.
So you could smooth that a little, smooth that somehow.
What do you mean smooth it?
Well, you have if the trigger is conceived as a filter with sharp cutoffs, then and you're afraid of losing stuff because you're throwing it away. Well, then sample what you would have thrown away. Take a little bit of the band.
Oh yeah, that's done actually. So this is called pre-scaling on triggers.
Okay.
So you take even completely random triggers, completely minimum bias, zero bias.
Okay.
You just take everything, but you take a very, very little of it. So that is always there in the background, but it's a very small fraction of the rate.
Okay. Have you seen anything interesting come back?
Well, ask Ben. What they can do with it.
Yeah, I'll say some more about it, I guess, in the next time.
Yeah. Right, so 4 quick details about the different triggers. This is just a random selection of things that I find interesting. That there's many other things that are interesting. So the first thing that I found interesting is that the Atlas fast tracker. So tracking is an expensive thing in general. So it costs CPU to reconstruct tracks out of space points. And if you do as much as possible on closer to the detector, then you can propagate this kind of information that you would not have at level 1 because it's too expensive to get. So the Atlas Fast Tracker is a way to do pattern recognition within associative memory chips that match the data to patterns that exist to make this process of pattern recognition faster. So this is what, in very, very brief, and you want to do this because if you have a track, then you can see if your collision event is coming from the vertex that has the most energy, so it's possibly interesting, or one of the other vertices. So this is one of the reasons why you want tracking as fast as possible, so you can discard pileup. There's another detail that is the LHC surely does not operate 100% of the time. There's times in between the runs, the physics runs, or there's machine development, or there's even between the different bunches, you could squeeze some time out. So why not storing the events, and then during that time, letting the computer farm do the processing? So this is what LHC does in various ways. You have a duty cycle that is about 30% of the time. This is an approximation. And then here you have a farm that where you store the data, you buffer it, and then you do the reconstruction for selecting more events while the LHC is not running. Another detail is that in the upgrade that is going to come in a few years' time, so this is not the big upgrade that Atlas and CMS are doing, it's an intermediate upgrade for us, but for LHCb it's a bigger upgrade. They're going to try and go completely triggerless. So try and have a software high-level trigger that will give you up to 2 to 5 gigabytes per second rate of storage. And this is because they essentially every event is going to be a signal for them, so they don't want to discard. They don't want to bias their selection. And so you move the entire analysis to the trigger, and you increase the capability of the HLT farm. So this is what Josh was saying. You try and do as much as possible that requires the full detector information at the high-level trigger, and then discard that information so that your event is smaller. So this is a takeaway point. Is if you think every event is interesting, you probably want to move towards a triggerless readout. It's pretty much impossible to do for Atlas and CMS for various reasons, but that's what LHCb is doing. And then another detail is what CMS and Atlas are also doing is to try and have full tracking information at the first level of the trigger. Because you need to reject, if you were taking events like you're taking now, the rate of events due to pileup would be already unsustainable. So you'd have to prescale and then you throw away events at random that are signal, no pileup, or noise that are pileup. So Atlas and CMS plan to provide tracks to level 1, so that you can already perform this selection at that level and reject events with pileup. So this is an example for CMS. They want to provide tracks at 40 megahertz. And they have 2 steps, and one is the on-detector rate data reduction, where you decide what stubs of tracks pass to the pattern recognition. So you already reduce the really large amount of tracks, based on the fact that if you have you use the curvature of the track and the relation with its momentum, so that you have an expectation that a track that starts here, if it has above a certain momentum, is going to end up in this region here. And you discard things that are more curved because they are lower energy. So this is already reducing a lot of the rate. And then there's a number of possibilities, they're still designing them, of real-time pattern recognitions that are mostly implemented in FPGAs or ASICs. So this is a nice summary of all of those. And then finally, before we start with the physics part, how do we decide what to record? We have a limited bandwidth. We have many interests. For example, Ben and I love jets. So jets are the products of quarks and gluons, and they fragment, and you see a spray of particles in the detector. This is also the thing that happens the most at the LHC. So if you decide to just listen to the 2 of us, you take 100% of jets, and then no one would record Ws anymore, because there's so many jets. We can do that. So what the experiment does is define a trigger menu that is generally defined at the beginning of a data taking period. And this is a menu that has to fit within the bandwidth that one has, so that 1 kilohertz. And you adapt the cuts of each of the objects based on their rates. So you'll see that this is the PT cut, so the energy cut at the HLT. Maybe let's look at the 2015 one. And you see that the threshold for the single electron is much lower than the threshold for the single jet trigger. And that has to do with the fact that jets are more frequent. So in order to have, and all this distribution fall. So I don't know if I have this. Okay, so maybe I'm saying obvious things, but this is the PT of an object, and this is the number of events that you have. And so if you just measure the PT of the object as a function, the number of events as a function of PT of the object, things are falling. So if you make a cut up to here, you're recording this part. So the rate of events after a certain cut is smaller than before a certain cut. So that's why you make a cut, the higher level trigger. And this cut is this threshold here. It's a more or less flexible kind of menu. So you decide at the start, but you can, if you see something very, very interesting, then you might decide that you want to devote more of your bandwidth to a given channel that you found interesting.
How long is a given data taking period?
So it depends on, there's chunks, usually chunks of data periods, and these are the ones where you make big changes to the menu, to the trigger menu. So it depends on the LHC schedule. It could be weeks, could be 1 week, could be a month. I mean, that order. But one single run is, I think, not more than a few days. You can also change in between the single physics runs, but it's less likely that you're going to, because it's a release, it's a software release.
It goes down,
yeah.
And then
you also want to test what's happening. Yeah.
Okay.
So there were some questions about explore, exploit in previous talks in other fields. Is there some sort of 1% save for just let's randomly save some data?
Yeah, there is.
So there's a menu of just random. Right?
Yeah, so there's random triggers that I've cut out. If you want to know everything about the Atlas triggers, it's over there.
How much does the 1%?
Yeah, it's not. It's really not. Like, it's really squeezing everything you want. You can.
It's 1% of the 1% of the stuff they say.
So one thing that I found interesting, and I don't know if Atlas or CMS do it. Atlas, I'm not sure. CMS might, but I don't know, have the information. Is that you can optimize this dynamically. So you just throw your optimization criteria to an MVA, and then you let the MVA decide on these cuts. So this is what LHCb is trying to do. It's a bandwidth division. But in any case, you risk two things. One is that you don't record enough events, because maybe the process that you're interested in produces jets at 200. And what you're doing below 360 is pre-scaling the trigger. So you're only taking one every 10, or one every 100, or one every million. So you're really shooting yourself in the foot if you really want that kind of signal. And the other problem is that if you're here, it's a single electron, single muon. These are single physics objects, so it's fairly generic. But what if it's an electron that doesn't quite look like an electron, that might have decayed far away in the detector and then has produced a shower of things? That's not an electron anymore, so you don't trigger on it. So these kind of classes of events, you risk missing them. And people are thinking about this problem. There was a workshop, I think about a year ago. So people are really worried about these kind of things.
Does every event correspond to a single collision, or can you have a kind of cascade of collisions that could together signal an event?
So every event has some contribution from previous and collisions before and collision after. So this is the basic.
Right.
But you can have physics models.
I think he's asking about the collisions out from the fundamental event.
So, I'm not sure you mean this.
The transformations that happen.
So if you have, I don't know, you have the two protons that collide, right? And then you get, I don't know.
Could you have 3 protons collide?
Yeah, well, it's less likely. Multi-party interactions happen, but you can. Yeah.
Could you get multiple proton-proton collisions at the same time in the same
Yes.
bunch of particles?
Yeah.
Yes. And those can contribute. So you can get an electron from one collision and an electron from another collision that can confuse the trigger. Yes. And there you typically use pointing back to the vertex to see if they were aligned, that sort of thing.
And
But-
imagine you could have scattering of the debris as well, right?
Yeah, that's also something that is always, but there's also models that actually impose that this happens. So new physics models where you have a particle that waits to decay and then decays a few bunch crossings after your collision has happened. So you find it on top of another collision, and this is inconvenient. So you look for this kind of events in empty bunch crossings. So if something just shoots up, then it might be a sign of those particles, or a cosmic ray. Right, so why should we do better? And because we don't know what to expect from new physics. And here is I take an expression from one of the talks on the gravitational waves on the first day. Your heart is broken if you lose data. So what do we do to minimize heartbreaks? You want to analyze as much data as possible, as fast as possible. So this is the paradigm shift that I was talking about, where you try and do as much data reduction, as much data processing at the trigger level so that you discard the information that you don't need to redo that. You can also save the data for later reconstruction. I'm not talking about this, but if you have the storage resources and you don't have the computing resources, just park the data somewhere. And then whenever the LHC is in a long technical stop, you reconstruct it later. And one can also implement more refined and unexpected trigger algorithms. So I point you to two local experts if you want to ask here. So let's move on to the real-time use case number 1. Why do we want to do this? So we see that the bandwidth is event rate times event size. So if you make the event size smaller, then you can take more events. That's very logical. And this is an important limitation when you have very high rate backgrounds and when you can't really select, because everything is interesting. And this is also important because low rate processes are what we've not actually looked for because we haven't had data to do it. And at the moment, the LHC luminosity will increase more than the energy. So this is the kind of process we want to look for. So we move from the asynchronous data analysis, where you record as much as possible and then analyze later, to a real-time data analysis, where you reconstruct and analyze the data right after it's recorded, and then you throw away all the information needed for the reconstruction. You just save the high-level physics objects. And yesterday we've heard keep only the science content. Somehow that's a similar thing. You're trying to keep the high-level objects, electrons, photons, things like that. There's problems in both, because the asynchronous data analysis, the problem is that the output is large and you're fixing it here. And the high luminosity, you always have to raise the threshold, so you're going to miss some physics. But if you want to do a very refined data analysis, then you need all this information. So you can't just go and say, I'm going to throw everything away, because you might regret it. And in real-time data analysis is great that the output is small, so you collect more data with less storage. But it does require more online computing power, so you have to reconstruct these events. You have to pass them through the high-level trigger, and you can't go back and re-reconstruct. So these are the two paths, though. If you have a decision, you always have to make a decision at the trigger level. So you have some unrefined data analysis. So it doesn't cost very much to use the same information that you've used to make the decision and just save that information in a special stream. And this is the analysis with trigger objects. And only if the trigger has passed, then you go to the standard stream where you record everything. So we have two different streams in Atlas CMS and LHCb. And it's very important that you do, at this point, that the reconstruction that you perform offline after you recorded the whole event is the same as the one that you do online, so that you can have the same quality of the objects. So this is very good in general, because you improve the trigger decision as well when you make these algorithms the same. It's not obvious that they are. And then LHCb has managed to do a full-on real-time calibration where the resolution is really the same. This is for tracks between online and offline. And this is possible thanks to the computing power of the HLT farms. So what's the use case here? You had a question?
It's sort of maybe going back to trying to look at the effect of luminosity in a situation. If you have a very low luminosity, but you are very lucky, and you can get single events in this particular detector, are there possible events that swamp the current design, single events that swamp the current design of the detector to detect, so that even if you capture, as this detector can describe those events, you haven't acquired the information to begin with the detector, or do you make the assumption that, well, of all the possible events, even the fuzzy ones around the edge, our detector could see one of those if it happened?
I think we make the assumption that we could see it. So we do have runs where we impose that there's only one collision. So we put the beams in such configuration that where you only have one interaction at the same time. I don't know if that answers your question.
Okay, and the detector is...
And the detector can see that, yeah. It can see either... The detector then, in principle, prefers not to have pileup. Okay. It would be nicer if, but we do.
And current theory and quasi-theory doesn't imagine any kind of interaction that would be invisible, that would be too complex for the detector to discern.
So it would saturate the detector readout, you mean?
Or be ambiguous in some sense. Because you weren't getting the right combination of spatial resolution and energy.
I don't know, I think it's possible. If you have particles, if you have a process that gives you particles that are too soft, for example, they all bend, and they don't actually get to your detector. So this is the kind of, there's theories where anything can happen, essentially. But then you can use different techniques. So you try and see if there's something in the initial state. So a proton, one of the partons of the proton has radiated a gluon, for example, and you use the gluon to tag the event, and then you see missing energy.
Yeah,
so
I'm just
could
trying
possibly
to characterize the physical assumptions built into this particular detector mechanism, and from which you start to degrade.
Yeah, so I think there are events that we are possibly missing because we are not doing the reconstruction right for those particular events. So things that the tracks that start too late, you might discard them because you think they're noise, but they're not actually noise. So people are thinking about that as well.
So that's a structural hole.
Yeah, but we're trying to patch all of this, I think. Right, so I'm not going to tell you what dark matter is, but I'm going to tell you a bit about dark matter mediators, because this is what we're trying to do with indirect detection, direct detection, and particle colliders. We're assuming that the dark matter is interacting with the standard model, and we're trying to look for the products of this interaction. So if you have a force, you will have a mediator. This is just looking at the contact interaction versus when you found the W in the Fermi interaction. And so one can look for this mediator in both invisible way, and this is one of the kind of events that maybe you were mentioning, that we don't see anything because the particles just don't interact in our detector. But you look for it with the initial state radiation from the quark, and then you look for the missing energy. But if the mediator has been produced from standard model particles, it will also decay in standard model particles. And for this kind of particular models, they're very, very simple, so let's not take them too seriously. But if you try and connect them to the relic density, then they have to, in this shaded region, and this is the mediator mass on the y-axis and dark matter on the x-axis, and what we want to see is the mediator, you see that there's, very, very quickly, the mediator masses above 100 GeV, 200 GeV start producing too much dark matter. So this is not quite a dark matter model anymore, because it doesn't explain the relic density. So there's a theoretical interest to look for low mass mediator. And how would that new dark matter mediator manifest? It will manifest like the Higgs boson, a bump, in this case of 2 jets, above a distribution of QCD that makes also 2 jets, but it's continuous, it doesn't have any features. And this mediator particle will appear with a bump that has a mass corresponding to the mass of the mediator particle. The problem, though, is that in this case, you can't quite distinguish what is coming from the mediator and what is coming from QCD. So the only hope you have is to have a very good resolution for your bump. And if you prescale the events, so you're throwing away at random, then you're really killing the statistical precision of this, because you're only taking these events and with a very large weight. So if the signal is small, then you can't see it. So this is what we're trying to fix here. There was an entire region of phase space where dark matter mediators were not, not dark matter mediators, but in general this resonance were not looked at. And the last experiments that could do it were CDF and UA2, and we were just looking above. So now with in Atlas we call this a trigger level analysis because it's a 3-letter acronym, so it's a TLA. CMS calls it data scouting, and LHCb calls it turbostream. But you can actually record only the information necessary for this search, that is jets, and use the information that is already available. So you take the jets at the trigger level, and you see that for a very small portion of the bandwidth, so this blue line here, you can take up a lot of the rate. So the rate of just jets is almost as big as all the other events that you take, simply because you're taking a very small event size. And this is the increase in statistics that you see. So this is if you were doing a prescale trigger search, and here you get everything unprescaled. And CMS has been doing this since ATV, and this is now a standard. And now we are actually able to fill the region that was interesting here. And then we're trying to think about what to do here, but we'll get there. This is the same plot as before, where there was a huge hole here. Now the LHC has filled that hole. And in LHCb, they look for something that is, sorry, I'm going a bit fast, but I guess we had a lot of discussion. The case for real-time analysis also has to do with dark matter connected particles. It's dark bosons. They're not exactly the same thing, but they have something to do with the mediators that we were looking at before. But you can also do measurements. You want to do charm physics as precise as possible, so you have to take, if you want to do a very precise measurement, you want to take as much statistic as you can and then beat the theory uncertainty. And this is one of the most beautiful results that I've seen this year, I think. This is the, they've taken an unbiased sample of the immune events with this technique. And you can see all the QCD resonance really, really precisely. And then in the places where there's no QCD resonance, they've tried to set limits because they've not seen any deviation on these dark boson particles. And the limit is here, and it's a very low rate that we're constraining here. So yeah, to finish with, oops, sorry.
Just saying, Babar actually did better in some regions?
Yeah, it does.
Okay.
Well, we can talk about that later, but it's also that is a really nice search, I think. Okay, so in the last 5 minutes, the monitoring. And in this case, we use the same definition as before. You want to do a data analysis as promptly as possible so that you can fix issues that could be either in your trigger menu or in your detector itself. So there are people that are on shift looking at the detector and checking, monitoring that the detector is taking data correctly, that the data quality is good. And you can take a decision that is you fix the detector, change the trigger menu. And the timescales involved here are from as quickly as possible when you're on detector, but for the data taking, you have more chances to reconstruct, for example, so it can go up to days. And this is how you can ask how much of the data that we take at the LHC can we use. And it's a fairly large fraction here. So this is what the LHC delivers, and this is the integrated luminosity on the y-axis. And the blue is, the yellow is what Atlas records, because sometimes you have inefficiency, your detector's not ready or something glitched. And the blue is where all detector was considered functioning and good enough. So there's not very much difference between these two curves. And this is how the monitoring is done. I'm sorry I can't go into too much detail, but it's a fairly complex system that involves both online and offline computing. So you have different data streams where you have a smaller data stream that you look at right away for checking the data quality. And then there's another loop that can be done in order to, for example, mask cells that are noisy. This is one of the things. And this is yet not completely automatized. And I think there is a lot that one can do with anomaly detection and with machine learning. And it's people are starting. LHCb is also starting. Do you really need a person that looks at these histograms and then tells you this is not looking right or this is looking right? Yeah, to an extent, but there's a lot that can be done automatically. So in LHCb, they have what is called robo-shifters. And this is something that I've been developing, I think, with Yandex. So there is some extent of machine learning that tells you what is the likelihood that this run is good or not, using all the information they have and training it on good runs. And the last thing is another, maybe more controversial way to do analysis, especially if you like blind analysis. So there could be a system that just looks at all the distributions, compares it to the best estimate you have from simulation of the background, and tells you if you have a bump or a signal or something. So this is what they call the TADA. I don't remember the acronym, but it's just performing a predefined data analysis and telling you if your Monte Carlo is agreeing with the data. And with this, they've spotted a lot of issues in the calibrations, for example. Not necessarily any new physics, but I still think it's useful. It's a web display-based analysis. Right, finally, I will conclude by saying that we're just starting. And we've taken, we're exploring the energy frontier because the LHC is at the moment the machine that has the highest energy, center mass energy, for making new particles in a lab. So we should keep using it. And this is Fabiola Gianotti that says, we have to exploit it because we've built it so far. So we have to actually run it and make the most of this data. And we are here. So and this is a log scale here. So we're going for 100 inverse femtobarn so far, I think, in total. And we have to go to 3,000 inverse femtobarn. So there's a long way to go. And how do we make the most of this information? And this is conclusions that we've drawn at this in 2015, but they're still valid to me, is that we can move a lot of simple analysis and searches to this lossy format where you throw away most of the information because you think that you understand the objects well enough. And you use these techniques to do a lot of the measurements. Now you do with the full data set and leave space for other things that might be more rare phenomena that needs a full reconstruction and so on. And then one always needs to monitor calibrations and conditions in real time and do it as well as possible so that you don't miss anything because your detector had holes or because your data taking wasn't optimal. And then finally, I'm particularly addressing those that think that the LHC is a dead end. There are some unknown experimentalists that think that. Yeah, sure, we have looked for low-hanging fruit, but it can actually hit us in the eye. And so we do expect surprises from the data set. We have problems to solve. And we, especially at the electroweak scale, that is a very special scale, that's where the Higgs boson was found, where the W and Z boson, in order to probe that scale with the, first with jets and then also with leptons, we will need this kind of data taking techniques because the rates of the data in that region are too high. And the last point is that we've seen in this workshop that there's the real-time decision-making challenges are cross-field. So there are ways to collaborate on tools and infrastructure, and I put here a few links to the HEP Software Foundation roadmap white paper that could be a first starting point to say, okay, we think what we need, this is what we've thought we needed in LHC for the next 20 years. What do other fields need? Are there parallels and so on? So there's forums to discuss this. So sorry for using all my time. I hope we can still have the coffee break. And thank you very much.
We have time for maybe a couple questions before coffee. Yeah.
This is a general question. This is way outside my area of expertise, but I've always wondered, like for the Higgs boson discovery, what significance or sigma level was considered the threshold for actually pronouncing that the Higgs boson had?
5, roughly.
And so why that threshold?
Good question. I think that's a very good question that you could debate for hours. And if you put a statistician there and a Bayesian there, and you have entertainment for days.
It's set really high, so I assume it's set so high. Yeah. It just makes me a little suspicious.
It's a sort of false positive rate if you think about it. It tells you how many thought experiments, so I'm being frequentist here, how many thought experiments you'd have to have and see the same amount of Higgs boson-like events if you just had background. So you can set that threshold as high as you want. It doesn't tell you that that is exactly the Higgs boson, but it's pretty high.
Well, that's the thing. Setting it so high, is it possible it's a misguided attempt to account for the fact that there may be other alternative explanations for that bump or whatever? But there's no way to quantify that. I mean, there's no way to quantify the a priori probability that that is indeed the signature of the Higgs boson and not something else.
I think you don't use the bump to tell it's a Higgs boson. So if you read the wording of the initial discovery was we found a new boson, no mention of the Higgs. Right. Because in order to see whether, I don't think I have the plot here, but in order to define that as a Higgs boson, you need to measure its properties. So this is a completely different suite of measurements that you need to measure the spin, you need to measure the charge, you need to check that all the couplings line up on what you expect, that your signal strength is the same in all the channels as you expect. So that gives you more confidence that it is actually a Higgs boson. But the bump by itself doesn't tell you anything.
There's a corollary in astrophysics, which was the quote-unquote discovery of dark energy via supernova was not announced as such. It was the discovery of the accelerating universe. Even though our thought was that it had to be dark energy propelling this, that was not said. What was said was we made a measurement in the universe that's accelerating. We also used 5 sigma. That is a standard thing. I think it's been around since the 40s or 50s in high energy physics. And I believe it's cultural more than anything else, is that some people, there were experiments in the past that released things early that turned out to be wrong. And so they established this 5 sigma.
Well, it's not 5 sigma statistical, to be clear, right?
Yeah, this is including systematics.
Yeah, including systematics as well.
Yeah.
So what does that mean?
Yeah, statistician, there's no meaning for a statistician between statistical and systematic.
Yeah. This is a systematic.
Like bias and variance. It includes a bias term.
It includes biases.
A model of biases.
And the known biases and maybe some accounting of the unknown.
That's where it gets, of course, very fuzzy. Is how do you
Exactly, and how do you do the statistics
How
to
do you do the
make that
correlations of this?
statement and all of that.
But there's people that have advocated doing varying, so having, this is a Bayesian person actually, saying how difficult is your analysis, then if it's more difficult, you get penalized by the number of sigma that you need to have. Right. So there are papers on the archive that say we should do that. But, you know.
So you emphasized that the fast trigger has to be close to the metal because you're going to be doing things right off the detector, and you don't want to be you're going to be at less bandwidth limited close to the metal. So I have like a million questions about that, but I will try to boil it down to one, which is that as you're going to want to make how much work is done on these hardware triggers in real time, like presumably every time you do some kind of upgrade, each of these experiments goes in and makes hardware changes in their hardware triggers. Like what is it like being adaptive? I mean, obviously these experiments are very adaptive and they're going to adapt further as they go on, and as physics hints appear, you're going to adapt. How much of that adaptation happens at the hardware level, and how does that work? Are you guys replacing the hardware triggers every upgrade? Or
I think you have to replace both the readouts because sometimes your detector itself is not fast enough to give the information to your trigger system. The trigger system is not something, it's not an intelligent, necessarily an intelligent thing. It just receives information, makes a decision. So how fast you get the information is important. So for that reason, sometimes you have to replace the tracking if you want to have a track trigger.
I see. And so is there constant hardware work at that level inside the system? As you go up in energy, you're also doing hardware work on the triggers?
Yeah, you tend to keep it constant when you can't access it because the LHC is running, so that you can't fix. But all the rest of the time, people are replacing.
People jump in and upgrade the hardware.
Yeah.
So that's a kind of real time, which we're not used to. But that is real time in some sense, because you will adapt those things to. Like it's real time because.
You mean there's feedback?
Because it's got.
Yeah, there's someone told you in the previous run the pile up is gone up to 400. So you need a completely different detector because it died. Yeah.
That would be cool to go into LSST and just totally change the filters.
Oh, believe me, I have plans.
Yeah.
The question is, do we need to change the CCDs?
Yeah, exactly.
Filters
Hot
are
swappable.
But changing the CCDs is more like changing the silicon, like detectors, which we don't do. We do that like once every 10 years.
Right.
Yeah.
So
whereas the hardware triggers is more
the hardware triggers, some of that stuff is off detector. So that's why we can like off detector. It's like meters away, so we can physically go and tinker with stuff.
I was being facetious. A paper just came out saying that it could be that all astronomical CCDs are messed up. So.
But, I mean, the other kind of hardware trigger question I have is related to the light cone thing, which is that you have this collision, and then the information from that collision is expanding as a sphere. The bigger your detector, the more of that sphere you have to integrate to get into your hardware detector. So it's a very interesting question of whether the hardware detectors could somehow be more local on the light cone. Because right now the hardware detectors have to integrate this whole sphere to make decisions.
But not necessarily. Yeah, I mean, I'm talking about an example that I guess is easy for me to understand, that is run one. I'm not really an expert of the track triggers, but there's ways to do it like that. But you can just look at the region of interest. So you have something that informs you of where most of the action is, and then just read that out.
Yes, right.
So like for instance, right now, the inner detector, like the innermost layers of our detector, they are not used for the hardware level trigger. We only use the parts that are far away from the detector to do the triggering, because we just can't read it out and process fast enough. And then,
right, I was going to ask about that too. I have a million questions, because you also have a light cone. It's a slower light cone inside your electronics.
Well, yeah, so the light cone it takes like 20 nanoseconds for particles to go through the whole thing. And it takes 200 nanoseconds to integrate the entire detector. So actually the first light cone is actually fast compared to like the bunch processing.
All right, let's thank Caterina again, and we can ask more questions.